Recall that the notion of divisibility we define as follows. Let b be an integer and p not equal to 0, a an integer. We say that b divides a if there exists an integer q belongs to z such that a is equal to bq. This is how we define divisibility. Now we are going to see some properties of this divisibility which will easily follow from its definition. Property 1. If a, b belongs to z, both non-zero, and a divides b and b divides a, then a equal to plus or minus b, or in other words, absolute values of a and b are the same. So what we are saying here is that suppose that we have non-zero integers a and b, and if we have a dividing b and b dividing a at the same time, then we have absolute values of a and b the same, or a is equal to plus or minus b. So how do we prove this? The proof is quite straightforward and just uses the definition of divisibility. So what are the things given to us? A divides b is given to us. Given a divides b, there exists q belongs to z such that b equal to a q. Now what is the next thing given to us? It's also given that b divides a. Given b divides a, there exists q prime belongs to z such that a is equal to b q prime. Now we already have an expression for this b. B is equal to aq. So if we substitute it here in the place of b, a q q prime. If we bring both these things, both a and a q q prime to the same side, we get a minus a q q prime equal to 0, or taking a outside, 1 minus q q prime equal to 0. But remember that we have assumed already that a is not 0. A is equal to no, a not 0 implies we have a product equal to 0, one is not 0, therefore the other one has to be 0. Therefore 1 minus q prime must be 0, or q prime must be equal to 1. Q and q prime are both integers, their product is equal to 1, therefore the possibilities are the following. Either q equal to q prime equal to 1, both are 1, or q equal to q prime equal to minus 1. So what happens in the first case? If we have q equal to q prime equal to 1, in the first case, q equal to q prime equal to 1, therefore b equal to aq equal to a. In the second case, q equal to q prime equal to minus 1, therefore b is equal to aq is equal to minus a. Therefore, in either of these cases, we will get b to be equal to a or b to be equal to minus a. Therefore, a equal to plus or minus b, or mod a equal to mod b. From what we just observed, we can make actually a simpler statement when the numbers are positive. So the statement is this: when a, b both are positive integers or natural numbers, and a divides b and b divides a, then we have a equal to b. Just remember one thing, that a and b are positive implies that modulus of a is the same as a, modulus of b is the same as b. Therefore, in the previous statement, we need to just substitute instead of mod a, we have to put a, instead of mod b, we have to put b. So the next property is the following. If A divides B and A divides C, then A divides B plus C. That means that A dividing two integers B and C gives that A divides their sum also. So proof is again going to be quite similar to what we have done in the previous problem. That means use the definition of divisibility. A divides B implies there exists integer q such that b equal to aq, or we will write q1, b equal to aq1. Similarly, a divides c implies there exists integer q2 such that c equal to a q2. So we want to see if a divides b plus c, or we have to express b plus c as a product of a and some integer. So what is b plus c now? B plus c equal to a q1 plus a q2, but that is equal to a into q1 plus q2. This is nothing but we can call this to be some q3, where q3 is an integer. So we have b plus c is a product of a and some other integer. Therefore, a divides b plus c. Therefore, a divides b plus c follows. We can in fact make a similar statement saying that if A divides B and A divides C, then A divides B minus C also. But instead of that, we can give a much more general version of what we proved. If A divides B and A divides C, then A divides alpha B plus beta C for any alpha beta z. And this alpha b plus beta c is known as a linear combination of b and c. This is known as a linear combination of b and c. So proving this is again going to be quite simple. Exactly the same argument. There is not much difference. A divides b implies there exists q1 belongs to z such that b is equal to a q1. Similarly, B divides C, A divides C implies there exists Q2 such that I'm shortening the proof. There exists Q2 such that C is equal to A Q2. Now, what is alpha B plus beta C? Alpha B plus beta C equal to alpha into B is nothing but AQ1, AQ1 plus beta into C is nothing but AQ2. So if we take this A outside, we will get A into alpha Q1 plus beta Q2. This we can call as some Q3. Therefore, we get alpha B plus beta C as a multiple of A. Therefore, A divides alpha B plus beta C. If we put in the place of alpha 1 and beta 1, we will get A divides beta plus C. If we put alpha equal to 1 and beta equal to minus 1, we will get A divides B minus C. All these things will quickly follow. Now we are moving towards the next divisibility property. And what was the number? 3. Now we will move to the fourth property, which says that if A divides B and B divides C, then A divides C. This property is known as transitive property of division. So proving this is once again going to be somewhat simple. A divides B. So to verify this, A divides B implies that there exists Q1 in Z with B is equal to that B is equal to AQ1. Now, A divides C implies there exists Q2 integer such that C is equal to AQ2. So if we, what we want finally? We want finally A to divide C. Now, oh, there is a small mistake. It's not exactly given like that. It's now given that B divides C. B divides C implies there exists Q2 integer such that C is equal to BQ2. But we want A to divide C. Therefore, we want to bring A and C together. But we have a relation between C and B and relation between B and A. So in the place of B, we will try to bring A here. So B is equal to AQ1. Therefore, this is equal to AQ3 if we want to call Q1, Q2 as Q3. Therefore, we get A divides C, and that's what we ended at. So we proved that divisibility is a transitive property. That means if A divides B and B divides C, then A divides C. Now we will verify one more property of divisibility. So the fifth one is the following. If A divides B, then A divides BC for any integer C. This is much more simpler. A divides B is given. A divides B, therefore there exists Q1 belongs to Z such that B equal to A Q1. So A divides B, therefore there exists Q1 such that B is equal to A Q1. Now we want to see BC. BC is equal to A Q1C equal to A Q1C clubbed together. Therefore, BC is a multiple of A or A divides BC. So that's actually a very simple verification. Now we have a small problem. Given integer A and B, we want to count how many multiples of B is possible just before A, or otherwise the number of B multiples we want to count that falls within the range 0 and B. Sorry, 0 and A. The statement is precisely the following. Let A and B be positive integers. Then the number of positive integers less than or equal to A and divisible by B is the integer part of A by B. Before going into solve this problem, we should probably explain what this simple integer part of A by B means is. So integer part of A by B, that's actually a function defined on the set of all real numbers, or it's also known as the greatest integer function or the floor function. We will define that function first. So the definition of floor function or greatest integer function. So this function, the greatest integer function defined on R. So this actually gives, by this symbol, we mean the largest integer not exceeding x. For example, suppose that we have x is equal to 5.2. In that case, greatest integer not exceeding x or floor of x is going to be equal to just 5. Suppose that we have 5.9. In this case also, it's going to be equal to 5. Suppose that we have 6. So this itself is an integer, therefore the greatest integer not exceeding 6 is going to be just equal to 6. Now suppose that we have to be careful. Suppose that we have minus 5.2. In this case, the greatest integer not exceeding minus 5.2 is not minus 5, because minus 5 is greater than minus 5.2. In this case, it's equal to minus 6. This is the only place where we have to be slightly more careful, because as far as positive real numbers are considered, the greatest integer part or the floor is obtained by just dropping uh, the decimal part. But when negative integers are considered, it is not just dropping the decimal part, but we have to go one more step ahead for finding the greatest integer. So I think the definition of the greatest integer function or the floor function is clear. Now we are going to make use of this particular greatest integer function or floor function in our problem. We are coming back to the problem. In this problem, we have to show that the number of multiples of b less than or equal to a, number of positive multiples of b less than or equal to a is equal to the floor of a by b. That's what we have to prove. So we are coming to the answer or proof of whatever we have claimed. Suppose there are a multiples of b between 0 and a. Of course, excluding 0 because we want only the positive multiples. So we have to prove that our k is nothing but the floor of a by b. This is what we have to prove. So the k multiples are going to be less than or equal to a. It will look like b to b, etc. kb, where kb is less than or equal to a. Now what we have to show is this k is equal to a by b. We have kb is less than or equal to a, or k less than or equal to a by b. That is obvious. Now what about a plus 1 into b? Is it going to be less than or equal to a? No, because if that is the case, then there will be k plus 1 multiples of b less than or equal to a. Therefore, this has to be strictly greater than a, or k plus 1 has to be greater than a by b, or k has to be greater than a by b minus 1. So we already have k less than or equal to a by b. Therefore, k a by b minus 1 less than k less than or equal to a by b. So k is an integer lying between a by b minus 1 and a by b. Just notice that the interval a by b minus 1 to a by b has length 1. So this interval, if we consider a by b minus 1 to a by b has length 1, and not only that, this cannot be this. So this has length 1, and this can contain at most one integer, and that integer we have already located, that is k. And the integer part of a by b cannot be anything less than a by b minus 1, because the greatest integer not exceeding a by b, it must lie very close to a by b. Therefore, this greatest integer part of a, the greatest integer part or integer part of a by b or greatest integer not exceeding a by b has to be k. Therefore, k is equal to a by b. Hence, we have verified what we have claimed. We will have one quick example for this particular problem that we have just done. Suppose we have one example. Suppose a is equal to 35 and b is equal to 7. So how many multiples of b are there just below a or equal to a? So the answer is multiples of 7 that are less than or equal to 35, that is 35 by 7 equal to 5. What are these multiples? These multiples are 1, sorry, 7, 14, 21, 28, and 35. This demonstrates the statement that we have just now verified.